Yes, hello everyone. Today we will start with the new chapter that is Unit 5, which is on oscillator and PLL. Okay. So this chapter basically deals with the design of CMOS oscillator, more specifically voltage control oscillators. Along with this, we will discuss some of the other circuits like ring oscillators, LC oscillators, and also the mathematical model for voltage control oscillators as well. Okay. And also we analyze about PLL in this chapter 5, right? So first we will start with the oscillator. We know that oscillator is a circuit which produces an constant oscillations or constant output frequency without having any input, right? So well, you see, oscillator are the integral part of many electronic systems. The application of these oscillators ranges from clock generations in microprocessor, like carrier synthesis in cellular telephones. It has a vast different topologies as well. Along with this, we have different performance parameters of the oscillators, so which we are going to analyze. While designing, we need to ensure that it should be robust, high performance, and to design this, we have an interesting challenges in this. Okay. So to analyze this, the basic concept of oscillators, we have to start with the feedback model. Okay. So in the feedback model, we have a mixer and an amplifier circuit which is represented by a certain transfer function. So we have a feedback with unity, say this is the case, this is the input x of s and output y of s. Okay. So this is the feedback circuit what we have. So this oscillators, we know that it produces a periodic output, especially in terms of voltage, without having any input. So how does it produces the output, sustained output indefinitely, right? So to analyze that, we are going to analyze this feedback system with respect to that. So this is a feedback circuit. We know the transfer function of this feedback circuit. The transfer function of this happens to be output by input is equal to h of s divided by 1 minus h of s. It's a unit feedback system, right? So in this transfer function, so how you're going to analyze to ensure that it will oscillate, this feedback system will oscillate, will give the sustained oscillation, right? So here, so if we make this h of s as 1, then what we get? We get output y of s without input, right? So this is the condition of oscillation, which is basically called as Barkhausen's criteria. Barkhausen's criteria for sustained oscillations. To mention it in other words, we need to have two particular condition. The one is, so this is magnitude, for example, this magnitude should be equal to 1, which means amplitude, right? And phase angle should be equal to 360 degree or integral multiple of 2 pi, right? So this is the angle condition. So only if these two conditions are satisfied, then you can say that these two are necessary condition to get the oscillation, right? And this both are valid at s equals j omega naught, that too particularly, where this omega naught is the oscillating frequency, right? So now this 360 degree is the total phase shift from input to output and output back to the input, right? So this 360 degree phase shift, what I am mentioning is the the total phase shift taking from input to the output and back to the input. This should be the condition, right? So, so far in the feedback circuit, you see in the forward path you have an amplifier, and feedback path you have in different types of circuit it includes. So usually in the forward path, the amplifier what you have, it usually have a DC phase shift of 180 degree. Okay, the forward path has a DC phase shift of 180 degree. So you need to provide an additional shift of 180 degree during the feedback path. Okay, so as I told, in the forward path you have a certain amplifier. Most of them will produce 360 degree and most of them may produce 180 degree depending upon the amplifiers, the common source amplifiers what we generally use, right? And in the feedback what happens, we have some kind of RC circuits preferably, right? In the RC circuits, that means radio frequency, in the RC circuit we have RLC network in the feedback path. These are the one which is usually selected to set the frequency of oscillations. Understood? These are the components what we are going to use in the feedback path. What are the components? That is especially R, L and C. So these are the components we are going to use to set the frequency of oscillation, right? Why we use this RLC in the feedback path? So that is because this RLC has very low impedance at all frequency, right? So this RLC has very low frequency or low impedance at all frequency except at resonance. This is the conditions what it exhibit, making use of which we get oscillation. Using this property we create oscillation, right? So remember this, the Barkhausen's criteria what we told, that is the amplitude should be or the gain should be equal to 1 and the phase shift should be equal to 360 degree is necessary condition. Okay, they are the necessary condition, but they are not sufficient condition to oscillate. Okay, understand this point, because so if we satisfy these two conditions, it doesn't mean that the circuit will oscillate. Say for example, I will give a circuit. So this is the circuit what we have. Yeah, we will have two inverters so that we have gain. So this what happens, each inverter will produce a phase shift of 180 degree and obviously you will get 360 degree or multiple of 360 degree. It will satisfy the phase and also the magnitude. The magnitude of the inverter, the gain of the inverter is very large, we know that, right? So even though it satisfies both the condition, what happens, your output will not be oscillating. Okay, so what happens, you don't have enough gain first thing and necessary phase shift. Both are there, you have enough gain and necessary phase shift, but it will not oscillate. It will, what happens, latch up. It will latch up to one particular voltage. It might be either VDD or 0, that means to ground, right? So likewise we will discuss certain circuits as an example to know that whether this condition is necessary or what are the other conditions is required to get the oscillation. Okay, so first we will take a simple circuit which is an common source amplifier, and we have single R and C here, okay, and this is the feedback, right. So what happens, will this oscillate? It will not oscillate. Why? Because the first thing is the DC phase shift you will get from input to output is 180 degree, and an R and C will give a maximum phase shift of 90 degree, even though in the ideal condition, okay. So it will not satisfy the condition of phase shift, so hence it will not oscillate, okay. So we will take another circuit, we will add another stage of common source amplifier, right, and we have two stage of R and C, and this is the feedback RC RC. So what happens here? So here from input to here you will get 180 degree, and from here to here you will get additional 180 degree. So your DC phase shift itself is 360 degree. If the DC phase shift is 360 degree, then it will latch up, okay, and upon this R and C, 2 R and C will give an additional phase shift of 90 degree, okay. So it will give an additional phase shift of 90 degree into 2, 180 degree. So this will not cause the sufficient condition to clear your phase shift. It is not integral multiple of 2 pi, okay. So this will also will not oscillate, and at certain point, that means if it is 360 degree, if you are looking at this particular point, it will not oscillate, or you can tell that it is oscillating at 0 frequency. It is latched up to 0 voltage or high voltage, okay. The output will be always 1 or it will be always 0, right. So in this both the cases you have a phase shift problem. So we will modify the second circuit again. So we will have the same two stage amplifier, okay. So this is RC and this is another RC, okay. So in the path we will have an inverter, okay. So for this 180 degree you can add another 180 degree phase shift by this inverter, so that it becomes an integral multiple of 360 degree, okay. So this is an ideal inverter which gives an phase shift of 180 degree. What happens? So since the gain is anyhow large and the phase shift is satisfied 2 times of 360 degree, one 360 degree DC phase shift from 2 oscillators, and 2 RC stage will give an additional 90 plus 90, and an ideal inverter will give an additional 180 degree. Even though it satisfies this, it will oscillate at infinite frequency, okay. So the oscillating frequency omega naught is infinite, very high, okay. So this will also not in use, you cannot use this to generate an oscillations, okay. So we will have another circuit where we have an additional common source stage. So you have 3 stage RC, VDD here. So now here what happens? Will this oscillate? it may oscillate. Okay, it may oscillate because anyhow this condition. Okay, so the condition, the frequency of oscillation, the gain should be greater than 1, and the phase shift from input to output and back to the input, that means the loop phase shift should be an integral multiple of 360°. Okay, because you have 3 common source amplifier, so you have 3 180° phase shift. Okay, so which you get 540, and you have additional R and C. Each RC will give a phase shift of 90°. So you have an excess phase shift, so that you can tune this R and C to produce an phase shift of 180° only. You can tune this R and C so that, so ideally you will get 90° phase shift from R and C if both the resistance and capacitance are ideal. Okay, but practically that will not be the case. So you can choose the value of R and C, or you can tune it, or you can choose so that it can produce a phase shift of 180°. Okay, so total it becomes 2 times of 360°, 720°, right. So if you choose this condition, then it will oscillate, right. So now how to choose that? That is what we are going to look at here. So we have a total phase shift from input to output. This each individual will get a DC phase shift from input to output of 180°. So you need additional 180°, that you have to choose it from the 3 stage R and C. Okay. So now first thing we will look what is the gain. Okay, the gain which is output by input, we have minus A upon 1 plus S by omega p. Okay, so where A is equal to Gm into R and omega p is 1 upon Rc, the slope. Okay, so this is the gain of single stage. So if you take it for single stage, that too only common source amplifier I have taken. Okay, so if you take it for 3 stage, what will get? You will get, yeah, in the earlier case it is minus, right, minus A by 1 plus S upon omega p whole cube. So each will produce a gain of A upon 1 plus S upon omega p, where your omega p is at particular value, where the phase is given by 1 upon Rc, right. So if you plot the graph of this, that is the gain h of j omega, the gain, what happens, your DC gain. So this DC gain will be how much? Minus Gm into R 3 times, because each stage will give. Okay, and since each has since I have taken the value of R and C of all the 3 stages to be equal, R and C of all the 3 stages to be equal, so what you get basically, I will take the RC to be same, and each will produce a decrease in the gain of 20 decibels per decade. So because of 3 poles at the same location, what you get? You will get minus 60 decibels per decade at where you have 3 poles which are equal to 1 upon Rc. At this point we have 3 poles, right. So this is your the gain plot. This is how your frequency response will be, the gain response of the 3-stage RC circuit. Okay. So if you look at the phase again, so if you look at the phase, that is h of j omega's angle, okay, with respect to the frequency. So you have a DC gain of minus 180 degree. So at minus one, at 180 degree, the output is out of phase. So at 180 degree you have, and 3-stage of RC. 3-stage of RC can produce 90 plus 90 plus 90. So this is minus 90. So this is 90 and this is 2 90s. So 3 R and C will get an total phase shift of minus 80 degree to plus 180 degree to minus 90 degree. Okay. So in this you have to choose the value of R and C somewhere at the pole where all the poles are located at this location 1 upon RC. What happens? It will oscillate. Okay. So this is the final phase where the each R and C will give a additional phase. For example, it will give an additional phase of 45 degree. Okay. So this is excess phase added. Okay. So we will calculate that phase. At omega is 1 upon RC, what happens? We have 45 degree produced by each added. So we will find out what phase the frequency is oscillating. Okay. So we have omega naught, which is an oscillating frequency. That is what we have to calculate. So h of j omega naught, h of j omega naught should be equal to 360 degree. This is the necessary condition. Okay. So phase is calculated by tan inverse of omega naught upon omega p, corresponding to this equation. Taking omega naught upon omega p, this is the phase given by each R and C. So you have 3 stage and that should give 180 degree, which should be equal to 2 pi. Okay. So your tan inverse of omega upon omega p, omega naught upon omega p is pi by 3. So tan inverse of pi by 3 is tan inverse of 60, root 3 it will be. So your omega naught will be equal to root 3 times of omega p. This is the phase at which you are getting an oscillation frequency. This is the phase which is contributed by the each R and C to get the oscillation which satisfies the phase condition of 360 degree. So we have the second condition, which is h of j omega, that is the magnitude should be equal to 1. Okay. So we have the gain expression a naught cube upon 1 plus, I am taking the magnitude here, so 1 square plus omega naught upon omega p whole square in the square root. So I am taking cube because you have 3 stage, and this overall gain should be equal to 1. Okay. So if you substitute this omega naught is equal to omega p in this, what you get? You will get a naught cube by 8 is equal to 1. So therefore your A naught should be equal to 2. This is the gain required for oscillation. This is another condition which has to be satisfied by that 3-stage R and C to get the oscillations. This 3-stage R and C, the gain, overall gain from input to output should be equal to 2. This is the condition what it has to satisfy in order to get the oscillation. Okay. So what happens if this A naught is not equal to 2? If A naught is less than 2, what happens? So the gain condition is not satisfied and it will not oscillate. So if A naught is greater than 2, what happens? The amplitude of oscillation keeps on increasing. Okay. So the amplitude keeps on increasing if it is greater than 2. At some, it will stop for the fixed value of A naught, but whatever it should be greater than 2. If it is less than 2, it will not satisfy this condition and hence it will not oscillate. Okay. So this is what we conclude, that having Barkhausen's criteria itself is not sufficient to get the oscillations, because we see the other examples as well where Barkhausen's criteria is satisfied, but it will not oscillate. There are many circuits like this. Okay. But other than that, other than satisfying this, you need to work on so that to ensure that you get oscillations, necessary conditions. You have to work additionally to reach that condition, necessary condition. Okay. So that's for today's class. We will continue it in the next.